Our next speaker in the session is Yuta Notsu. So Yuta, please go ahead and share your screen.
Okay.
And Yuta will tell us about blue asymmetries in Balmer lines during mid-M dwarf flares.
Can you see my screen?
Yes.
Okay. Thank you for introducing me. My name is Yuta Notsu and I'm a postdoc at the University of Colorado Boulder. And in this talk, I will present about our recent results on blue asymmetries in Balmer line during mid-M dwarf flares and the causes of these people. So already there are some talks on flares, but I start from the introduction on solar and stellar flares. Flares are magnetic energy released in the solar and stellar atmosphere, and strong emissions, especially UV and optical and X-ray, are observed, and mass ejections also occurred with flares. And recently, many updates from statistical studies of Kepler and test data are done, but growing interest on the effects of flares on planets through high energy emissions and also strong plasma ejections. But among various interesting aspects of stellar flares, one important topic is the line profile asymmetries of chromospheric Balmer lines during flares. Recent exoplanet survey data have shown that there are many asymmetric blue shifted spectra from snapshot data. For example, like this. This is the H-alpha line profile from a lot of snapshot data by MDOS. And these data suggest these blue asymmetry, blue wing enhancement, might be common events among MDOF flares. And there are growing interest. These blue asymmetries are really possibly related with stellar mass ejection or so-called coronal mass ejection, CMEs. But these are only from snapshot data. So we need time-resolved spectroscopic data to investigate more details. So then we have conducted spectroscopic campaign observations of mid-M flare stars. We use several spectroscopic telescopes, but mainly we use the Apache Point Observatory SL spectrograph. Simultaneously, we conducted photometry, mainly using ArcSat with U and G band filters. And for some nights, we also use the test data. In total, we have conducted 34 night observations, including 25 night observations at APO. And in total, 46 flares in H-alpha lines are detected from the 34 night campaign. And at least 8 events among these 46 flares showing clear blue asymmetries. And we already reported one event in a paper this year, and preparing other 7 events in a paper in a preparation. And first, these are overall light curve for some nights, and of H-alpha data. And as you can see, there are many flares almost every night. All arrows corresponding to flares. And from YZCMI, Rachel talked about this stuff. And there are many flares, but not only flares, but also rotational modulations of probably from active region emissions are also seen. So this can be also studied, and interesting to compare with TESS or other light curves. But in this presentation, I mainly focus on these one of these 8 events, because there are 8 events. So in this presentation, I focus on one interesting event showing blue asymmetry. Okay, let's go into the detail of one blue shift event. And this event is a non or possibly weak white light flare with shift from blue to red asymmetry during long flares. Now let's see the details. The left panel is H-alpha and H-beta equivalent widths for one night, or YZCMI. And the right panel is ArcSat photometric data of YZCMI with U band and G band. And left panel is taken from SL, or 3.5-meter telescope, and the right panel is taken from a ArcSat flare camp. And we use a multicolor script, and thanks to this script, we can use changing. We use a rotating filter wheel, and we can take U band and G band both almost simultaneously. And in the left panel is a light curve of H alpha, H beta equivalent widths. As you can see, there are Balmer line flare with duration over 4 hours. Actually, flare not end at the end of the observation time. And but in white light, there are some small peaks in U band, but not so long H alpha like changes. So white light emission is very weak during this long H alpha flare, H alpha Balmer line flare. And yeah, let's see the profiles of during this flare. And first, in the early phase, this is corresponding to time 1, and also later phase here. And the early phase line profile, H alpha line profile is plotted in a blue line here, and later phase is plotted in a red line here. And the difference between the quiescent profile is shown here in the bottom panel. And as you can see, early phase, blue wing is more enhanced. But in the later phase, red part is red wing is more enhanced. Red wing of H alpha line is more enhanced. So this can be correspond to red asymmetry. Oh, sorry. And yeah, so early phase blue asymmetry is observed, and later phase red asymmetry is observed. And this is a color map of difference profile, color map of this difference profile, difference from quiescent profile. And as you can see, in early phase, time versus wavelengths, and the early phase, blue asymmetry is clearly observed, and later phase, red asymmetry is clearly observed. So there are some shifts from blue during flares. There are some shifts from blue to red. So some kind of plasma movement occur during these long time scale flares. Okay. Now, and so in total, 8 blue asymmetry. This kind of 8 blue asymmetry events, or actually some blue asymmetry events duration is a bit shorter, and some events are longer. And blue asymmetry of Balmer lines can be commonly seen during mid-end flares. But still, cause of blue asymmetry in Balmer lines still include some mysteries. This can be possibly cool upflows in flaring atmosphere, because if there are upflows because of Doppler shifts, blue shifts can be observed. But there is another possibility: cool mass ejections called prominence eruptions related with CMEs. The cooler part of the core of mass ejection can be observed in H alpha. No, but more studies comparing other lines and also comparing with UV lines should be done in future. Now, okay, but in this study, by assuming that blue asymmetry were caused, of course, this is assumption, by assuming that blue asymmetry were caused by prominence eruptions, the second possibility, we can estimate the mass and the kinetic energy of the upward moving materials by fitting the blue shifted spectra, different spectra, not like this. And then we compare mass and kinetic energy of blue shifted material with corresponding solar CMEs, the solar prominence eruptions. And our data are plotted in a red point, and some previous studies are plotted with other symbols. And the left side values are solar events. And as you can see, the estimated mass versus flare energy, mass are comparable to expectation from the empirical relation between flare energy and the mass of upward moving material for stellar flares and solar CMEs. Maybe this one relation, but in contrast, the estimated kinetic energy is much smaller than expectation from solar, a bit smaller than expectations from solar CMEs. Now, but this could be understood by the difference in the velocity between solar CMEs cool prominence eruption, because these black points are focused on the outer part, solar CMEs, but these H events observed in H alpha is more inner part and or earlier part of the events. So this could be understood by the difference in the velocity between CMEs and cool prominent materials, but this should be investigated more in detail. So in summary, blue asymmetry of Bellman lines can be commonly seen during mid-Mdorf flares. And in our event, our observation, 8 blue asymmetry events among 646 flares. However, it is still not clear how blue asymmetries occur. So we need more observations comparing with other chromospheric lines and also UV lines. And mass and kinetic energy of mass ejection could be estimated from blue asymmetries. And possibly consistent with solar relations, but velocity difference should be investigated more. So in future, more observations, including or more analysis from our data, actually APO data, including other lines, other chromospheric lines. And we plan to observe other spectral types and the comparison with other wavelengths through big campaigns. And also, University of Colorado Boulder is working on EUV dimming stellar CME observations. So this in future, in 5 or 6 years. So this can be collaborated. So that's all. Thank you very much.
Thank you, Yuta.
Thank you. Thank you.
So again, James Davenport, you have the first question.
Great work, Yuta. I'm wondering if there's an obvious viewing angle component to the difference in the kinetic energies, the velocities that are coming out. Do we have a sense for if the velocities we expect are isotropic?
Yeah, this can be affected. So viewing angle is affected, probably a factor. So yeah, actually, I have not investigated in this for this point more. So maybe we should compare with some modeling, toy model or something like that. Thank you.
Yeah, thank you.
So Yuta,
Yep.
the example you showed with the blue asymmetry, the light curve wasn't doing anything special. What about the other events that have the blue asymmetry? What do those light curves look like?
Sorry, I have not prepared the figure, but for example, in this event, blue asymmetry is very long for 2 or 3 hours, but some events just very small, shorter peak, and blue asymmetry is only seen at 10 or 20 minutes. So the time scale has a lot of variety among 8 events.
But then what is, like, for example, the U plus G light curve you showed? Are they consistently flat? That is, there's no white light flare while there's the blue asymmetry?
Among 8 events, only 1 event showing a very strong white light. So I don't know white light is a key factor or not, but yeah, sorry, I don't have a clear answer yet. But yeah, 1 event has a strong white light emission among 8 events.
Okay, so one quick question from Russet.
Yeah, that plot that you were just showing, the color map, it looks like the blue asymmetry preceded the flare. Is that real?
Maybe there are some tiny flare here. I don't define this because we didn't catch early phase, but this can be related with this small flare.
Okay.
Yeah.
Great. Well, thank you again, Yuta.
Thank you. Thank you.